Good morning, everyone. We're going to tackle our lesson for first quarter, Earth's internal heat. Earth can be divided into three main layers: the core, the mantle, and the crust. Each of these layers can be further divided into two parts: the inner and outer core, the upper and lower mantle, and the continental and oceanic crust. Table 1 shows the characteristics and chemical composition of each layer. Earth's temperature increases with depth, but not at a uniform rate. Earth's geothermal gradient is 15 degrees to 30 degrees Celsius per kilometer within the crust. It then drops off dramatically through the mantle, increases more quickly at the base of the mantle, and then increases slowly through the core. The temperature is approximately 1000 degrees Celsius at the base of the crust, around 3500 degrees Celsius at the base of the mantle, and approximately 6000 degrees Celsius at Earth's center. In spite of high temperatures within Earth, mantle rocks are almost entirely solid. High pressures keep them from melting. The red dashed line in Figure 1 right shows the minimum temperature at which dry mantle rocks will melt. Rocks at temperatures to the left of the line will remain solid. In rocks at temperatures to the right of the line, some minerals will begin to melt. Notice that the red dashed line goes farther to the right for greater depths, and therefore greater pressures. Now compare the geothermal gradient with the red dashed line. The geothermal gradient is to the left of the red line, except in the asthenosphere, where small amounts of melt are present. Convection helps to move heat within Earth. The fact that the temperature gradient is much lower in the main part of the mantle than in the lithosphere has been interpreted as evidence of convection in the mantle. When the mantle convects, heat is transferred through the mantle by physically moving hot rocks. Mantle convection is the result of heat transfer from the core to the base of the lower mantle. As with a pot of soup in a hot stove, the material near the heat source, the soap at the bottom of the pot, becomes hot and expands, making it less dense than the material above. Buoyancy causes it to rise, and cooler material flows in from the sides. Of course, convection in the soap pot is much faster than convection in the mantle. Mantle convection occurs at rates of centimeters per year. Convection carries heat to the surface of the mantle much faster than heating by conduction. Conduction is heat transfer by collisions between molecules and is how heat is transferred from the stove to the soap pot. A convecting mantle is an essential feature of plate tectonics because the higher rate of heat transfer is necessary to keep the asthenosphere weak. Earth's mantle will stop convecting once the core has cooled to the point where there is not enough heat transfer to overcome the strength of the rock. This has already happened on smaller planets like Mercury and Mars, as well as on Earth's moon. When mantle convection stops, the end of plate tectonics will follow. Models of mantle convection. In the soap pot example, convection moves hot soap from the bottom of the pot to the top. Some geologists think that the Earth's convection works the same way. Hot rock from the base of the mantle moves all the way to the top of the mantle before cooling and sinking back down again. This view is referred to as whole mantle convection. Other geologists think that the upper and lower mantle are too different to convect as one. They point to slabs of lithosphere that are sinking back into the mantle, some of which seem to perch on the boundary between the upper and lower mantle, rather than sinking straight through. They also note chemical differences in magma originating in different parts of the mantle, differences that are not consistent with the entire mantle being well stirred. Why is Earth hot inside? The heat of Earth's interior comes from a variety of sources. These include the heat contained in the objects that accreted to form Earth, and the heat produced when they collided. As Earth grew larger, The increased pressure in Earth's interior caused it to compress and heat up. Heat also came from friction when melted material was redistributed within Earth, forming the core and mantle. There are two major sources of heat flow from Earth's interior. Heat produced through the radioactive decay of long half-life radioisotopes in Earth's interior, radiogenic heat, accounts for about 50% of the present total heat flow. Primordial heat, that is, heat loss as Earth continues to cool from the heat generated by the accretion processes that form it, accounts for the remaining internal heat flow. A major source of Earth's heat is radioactivity, the energy released when the unstable atoms decay. The radioactive isotopes uranium-235, uranium-238, potassium-40, and thorium-232 in Earth's mantle are the primary source. Radioactive decay produced more heat early in Earth's history than it does today, because fewer atoms of those isotopes are left today. Heat contributed by radioactivity is now roughly a quarter what it was when Earth formed. Importance of Earth's interior heat flow. The present temperature of the mantle just under its oceanic crust is 1,410 degrees Celsius. The current high temperature of the upper mantle means that the upper mantle material has a low viscosity, flows more easily. A familiar analogy would be the difference between a cold stick of butter and a stick of butter that has been melted in a saucepan. The mantle's low viscosity, the tectonic plates in Earth's crust are able to move relative to another. A feature of Earth for the past 3.8 billion years transformed Earth from a water world, where only water existed on its surface, to a planet possessing both surface oceans and surface continents. The combination of surface oceans and continents and enduring, strong tectonic activity established the biogeochemical cycles that allowed Earth's surface temperature to be sustained at an optimal level for life in spite of the ongoing brightening of the sun. The same combination has been recycling many of Earth's life-essential nutrients. Without Earth's enduring, strong interior heat flow, at best, only microbial life could have existed on Earth and for only several million years. In that event, microbial life never would have been able to physically and chemically transform Earth's surface environment so that plants, animals, and humans could exist. The current cooling rate of Earth's mantle is 70 to 130 degrees Celsius per billion years. This cooling is slow enough to pose no short-term threat to any current life forms. The cooling does imply, however, that Earth's mantle will become more viscous. Eventually, it will be 16, so viscous that plate tectonic activity will shut down. When that happens, advanced life and eventually all life will go extinct. The Earth's unique, strong, enduring interior heat flow enables it to have both a solid inner core and a liquid outer core. Earth's liquid core is almost entirely comprised of the ferrous elements iron, cobalt, and nickel. These easily magnetized elements driven by convection currents in the outer core explain why Earth has sustained a powerful magnetic field throughout at least the past 3.7 billion years. This powerful enduring magnetic field has shielded Earth's surface life from deadly high-energy particles flowing in from the sun and equally deadly high-energy cosmic rays. Without the shield, solar radiation would have sputtered both Earth's atmosphere and Earth's surface water into interplanetary space. Thank you for listening.